1.3 kilopascals. Initially, the house is at a uniform temperature of 10 Celsius. Now the electrical heater is turned on, and the heater runs until the air temperature in the house rises to an average value of 22 Celsius. Determine how much heat is absorbed by the air, assuming some air escapes through the cracks as heated air in the house expands at a constant temperature. Also, determine the cost of this heat if the unit cost of electricity in the area is $0.05 per kilowatt hour. If we want to discuss the question, we should look at what we're given and what they are asking us, right? So ultimately, they're asking us to determine the heat generated and how much money we're paying for that heat. And we're given the area, the average height. We're also given the change of temperature, and we're asked to assume the following. So we have constant pressure, and we know that at constant pressures, we can use CP, right? So what we're going to do, we're going to go back to our knowledge in thermodynamics, and we're going to assume that the energy is conserved. Okay, and so we're going to write the first law of thermodynamics. Now, after we write the first law of thermodynamics, we're going to have that Q minus W is going to be equal to the change in internal energy, okay? And after we take the work to the other side of the equation, like we discussed in the last session, we're going to have that the heat that's coming inside of the house is going to be MCP multiplied by delta T. Now, another assumption we're making is that the heat loss from the outdoors is also negligible during heating. And what that means is that we are not losing any heat during the heating process. So if we want to calculate the total energy generated by the heat, we shouldn't consider any losses. Now, after we write down that equation, we notice that we don't have the mass. Now, but we do have the volume, and we can calculate the volume using the area multiplied by the average height. After we get the volume, we can calculate the mass using the ideal gas law, because air is an ideal gas, and we can use that M is equal to PV over RT. This R value you can find out from the chart if you want the mass, what units and what value to write. And after we get the mass, we just apply the rule that Q is equal to MCP delta T. Now, the CP value of water is also known. You can look it up from the tables in the book. And what we got at the end is 9,038 kilojoules.
Sorry, you mean the AC for the air, not the water, right?
Yeah, sorry, for the air. Yeah, exactly, sorry.
Okay. I have a question. Yes, go ahead, continue.
Okay, so the last step is just to multiply the conversion factor by 1 over 3,600, because if we want to go from kilojoule to kilowatt per hour, we just multiply by 1 over 3,600 and then multiplied by 0.075, and we get that for him to change the temperature of his house from 10 to 22, he's going to pay $0.19.
We have a Q, right? It's 25.
Yeah, it's 25. Yeah, it's the power.
We can say it's 25 directly because there's only heat generated from the work, right? Like there's only.
Yeah, it's because this guy here is insulating. So there is power inside here, whether it's a resistor or whatever it is, and there's only one way to go. That power to go, so it's just going to be
great. So do we have to like write the first law of thermodynamics, or can we say it's equal to Q directly?
Yeah, actually, that's brings another thing. You can say it's Q directly, but it's not exactly 25. It's half of 25. Can you tell why?
Why it's half of 25?
Because it's going in two directions.
Exactly. Yeah.
The area is good. So we plug in the numbers and we find the temperature at the surface to be around 64.7 degrees Celsius.
Well, so just to be clear, what they are asking, they're asking for the temperature of the surface, so the temperature of the aluminum surface.
Yes, they're asking for the temperature of the aluminum surface.
And what we did was that we calculated the total heat generated first, then we calculated the temperature using the rate of heat. Yes.
Yeah, okay. And we calculated the area, and then we used the formula to find the what's it called, the temperature at the surface. We know that the temperature at infinity is going to be the temperature of the temperature released, which is 25 degrees Celsius. The temperature that's released around.
I'm sorry, Ward. I think I missed. How did you get the area? I mean, the area. Did you consider the area of the transistors, or is there something I missed?
No. We're using the area of the aluminum plate, which is provided above, which is 22 centimeters by 22 centimeters.
Oh, okay,
we convert it to meters, and then we use it in the formula. So we're trying to find the temperature of the surface at the aluminum foil, not using the what's it called, the transistors as a reference. So all these calculations are for that what's called the aluminum plate.
Oh,
so is that the total area including the transistors, or with the transistors not in them?
No, it's just the area. It's flat area. We're not talking about volume. We're talking about the surface area, which is 22 by 22.
Which is, guys, the contact. There's like the contact area, because that's where the heat is transferred, on the contact area between the aluminum plate and the resistors.
Okay, so in your equation next to the area of the surface, this is K, right? The thermal conductivity.
Yeah, the heat transfer coefficient, which is 25 watts per meter square Kelvin.
Okay, great.
What's the thermal conductivity? We didn't use it in this question, right?
No, we used heat transfer coefficient.
Oh, heat transfer coefficient, which is H. We don't use K here.
We didn't use K.
Yeah.
So we did not use the thermal conductivity in this question. We used the heat transfer coefficient.
Yeah.
Okay.
So can someone tell me what's the difference? So, like, because I'm looking at the units, and I think the difference is that it's only like divided by length as well.
Well,
yeah, we'll divide by the area, I think. The heat transfer coefficient is per unit area.
Yeah, so basically H is
the entire steel tank to be at 0 Celsius, and thus the thermal resistance of the tank to be negligible. Determine the rate of heat transfer of the iced water in the tank, the amount of ice at 0 Celsius that melts during a 24-hour period. The heat of fusion of water at atmospheric pressure is given as معطينا it's equal to 333.7 kilojoules per kilogram. The emissivity of the outer surface is 0.75, and the convection heat transfer coefficient of the outer surface can be taken to be 30 watts per meter square Kelvin. Assume the average surrounding surface temperature for radiation exchange to be 15 Celsius. Okay, so we're going to be working on the following assumptions. So we're working under steady state operations, right? The thermal properties of the tank and the convection heat coefficient is uniform, and the average surrounding surface temperature is 15 Celsius. The thermal resistance of the tank is negligible, and the entire steel tank is 0 Celsius. So when we want to solve for the outer surface area of the tank, we're going to say that the area of the surface is going to be pi r squared, or in this case, it's going to be pi d squared, which is going to be pi into 3.02 meters squared, and it's going to be 28.65 meters squared. Now, where did we get this number? It's because we had 3 meters at the beginning, right? And the spherical tank was made of 1 centimeter thick stainless steel. So if you add the 1 centimeter from both sides, you can get the area of the surface.
I have a question.
Okay.
Can you explain the types of heat transfer in this question, in this problem?
Okay, so we have 2 types of heat transfer in this question. First of all, we have convection. So convection is defined as when heat transfers from the surroundings. So, for example, here from the air to inside of the object that we're studying, and we